As I mentioned in the last video, the next task was recapping, and I want to just explain why I got so excited when the FM was working. As I said in the last video, when you have a radio that sort of works, it's working from the start, or at least it sounds like it works from the start, you can then use it to compare everything you do after that, and it helps you to avoid major mishaps. You can actually screw up a radio completely when you do the recapping. And the thing to do is not to do a whole lot of recapping before testing it. So what I do is I do a section, switch it on again, test it, compare to what it was before. And as you do that, you'll notice that if there's anything wrong, you can go back to the part of the circuit that you've just changed, the capacitors you've just changed, and see if you haven't forgotten something there, or soldered in the wrong place, or desoldered something that shouldn't have been desoldered. So what I've done here is I've started at the end, in other words near the speakers. These two are the two output transformers, those little guys, and they have a pretty, well, not really complex, but they've got a pretty big capacitor network over there. And these are those capacitors that you saw on top of the transformers. And I'll show you on the circuit what I've done next. The other thing is, when I'm doing this, as I'm doing this, I take the opportunity to try clean up around what I'm working on. So those transformers have now been totally cleaned. The phenolic pads at the top, or those phenolic strips at the top, have been cleaned with isopropyl alcohol. And so you basically doing two jobs at once. When you get to the end, you don't have to go clean under components that you've already changed. And when I did this change, I switched it on again on FM, and I discovered another little problem. As you can hear, the FM is working, and what I've noticed is that the volume is noticeably higher. So obviously those capacitors that were the ones that I swapped over there, and two on the inside, which I'll show you, were doing something to the sound level. And that's quite normal. If they leak across the transformers, you're getting less power or less signal going into the transformers. Now I'll explain what these components do in a second, but I want to show you something else. I was trying it out like I'm doing now, and suddenly the sound went off. It went very, very low. And what I do then is, you can do various things, but what I do then usually is I start wiggling the tubes. And when I got to this guy, if you see, sound is gone. It's back. So I know that that tube socket is dirty. Now that's obviously something that you expect anyway, but you do use these phases to make note of things you have to repair, and you can actually do it straight away, or you can make a note to do it in the future. And the reason I like doing it in phases like this is that it does help you to track other problems down. Instead of going looking for it theoretically, you actually get a practical view of what is going on. The other thing that I've noticed is that some of the pre-selection switches down here, the tonal ones, are stuck. Not stuck, but they don't always make release too well. So again, I went in there and I sprayed some contact cleaner and activated them, 20-30 times each. And so I've got that little problem sorted. So as you see, this is not a linear progress. It's not a linear process. You literally go along step by step, try and follow an order, which is what I try to do. And if you do that, you'll find little things that you repair along the way. Now, for example, this light bulb is fine, that one's dead. I could have swapped it already, but I know that I'm going to remove this whole front cover for cleaning, so I didn't do that yet. But I have started cleaning some of the chassis at the back here with isopropyl alcohol, and usually by the time I get to the end of the electrical restoration, a hell of a lot of the cleaning part has been done already, which makes it a lot easier. To actually sit down and do a cleanup job of one of these radios with nothing else is boring as hell, for me anyway. So that's what I like to do. Go along. Let me show you the inside of this stage that I've done. There you see those two yellow capacitors that have been swapped out. These are very, very difficult to get at. You've got to be very careful when you desolder these things because they've got pretty thick leads. So if you put too much pressure on, you can actually break the contact that it's on. And you really don't want to do that. So take it easy, very slowly, one at a time. Don't look at the clock. If you do, you're in the wrong hobby. So those two form part of that end circuit by the transformer, which I'll show you now in the schematic. When we look at the schematic, we'll notice this capacitor network across the main transformer. And this thing is very interesting. The way they've done this is very interesting. And it's actually beneficial, I think, to have a look at the overall audio stage and just follow through a little bit of how this works. And they call this three-channel stereo. So it's basically a left, right, and a 2+1, left, right, and bass system. And it works very well. This is the bass speaker, and then you've got your left and your right speaker, or the other way around. It doesn't matter. And the way this works is with one set of output tubes, you're creating three channels. Your left channel, your right channel, and your bass. Because the bass is not really directional, it's the main speaker in the middle of the radio, and this one pumps out most of the bass power. The side speakers are used like satellite speakers, and they produce the mids to higher frequencies. Okay? Now, the way this operates is described very, very well in an article in radiomuseum.org, which I'll link below. And if you're interested in this sort of thing, you should really go and read it because it's very, very interesting the way they've set this up. But I'll just very briefly describe it. What we have here, this first transformer, the main transformer, this is run in push-pull. Typical push-pull where you have this pentode over here, in push-pull configuration. The B plus is coming up the middle as usual, and then it goes through to the anode of that pentode over there, and again it comes through here to the anode of that pentode over there. So to understand how the central part works, consider this as short. Consider that this transformer and that transformer is not even there. Okay? They are, but imagine they're not there. Just a direct connection. So what you've really got is a typical push-pull configuration. And the way it works is as a normal push-pull transformer with one slight difference. It has a capacitor network across the primaries. And what you see here is you've got a big capacitor. This is a 0.1 microfarad. It's one of the yellow ones at the top. There's the other channel, 0.1 microfarad, yellow one at the top. These two inner ones are 10 nanofarads, and they are the two yellow capacitors on the inside that I showed you. And across the smaller capacitor is a switch, which is normally open, and that is a stereo switch. So that's activated when you push stereo. When you don't select stereo, this switch is open. So what you see here is the signal will see a capacitor across the primary, but a very low capacitance because you have 100 nanofarads in series with a 10 nanofarad. And the result of those two in series will be something like 7 or 8 nanofarads. Okay? So most of the frequency band, frequency spectrum, actually goes through this primary. So you hear it here. Okay? And this transformer, being push-pull, is driving most of the power because the lower notes, the lower frequencies, will have the most power content. But because it's push-pull, it can afford to be a smaller iron core, so a smaller transformer doing the job of a bigger one if this was single-ended. So you have a normal configuration where most of the power, most of the frequency band is going through and is getting induced into the bass speaker. Now when you push stereo, just looking at the central speaker for now, when you activate stereo, those switches close. Okay? Now bear in mind this is the left and the right, so those two switches close, and what you have now, because you've shorted out this capacitor, these two capacitors, the smaller ones, with that switch, you now have a situation where this primary, or these two primaries, this is a primary with a center tap, has a very big capacitor across it, 100 nanofarads across each side. And what this does is it acts like a low-pass filter. It acts almost like a crossover network on your speaker system at home, hi-fi speaker system, which means that it'll pass only lower frequencies through here because the higher frequencies will bleed through the high capacitor. And the result is that you have a lot less higher frequencies being induced in this transformer because they are being bled through. So you have a cut on your frequency chart, and your frequency range. This has a much lower cutoff frequency. Probably, I'm guessing now, but probably 150 hertz or so, 200 hertz maximum. What happens is the rest of the signal has to be produced somewhere else. And the place where it's produced is on these two outer transformers. Now, if we look at this one here, this transformer, although it is in the series path of that bigger one that we saw, is effectively being run in single-ended mode. So it is a smaller transformer, much lower inductance, and because it's driving sort of mid to higher frequencies, it can afford to be much smaller. It doesn't have to produce that much power. You still have a 1 nanofarad capacitor across it, which just takes off the higher frequencies. I don't know what the cutoff range is here, but what will happen here is this transformer will see or transfer to the speaker those frequencies that were bled from the top one through that capacitor. So it will see those frequencies and produce them on the speaker, but it will still cut out the very, very high frequencies, which will then be produced in the electrostatic tweeter, which we'll see in a minute. That's the left channel, okay? The right channel, I'm not sure if this is left or right, doesn't matter. The other channel is basically the same. You have the same situation here where this transformer is being run as a single-ended transformer for the mid to higher frequencies. And it really comes into play and becomes more obvious when the stereo button is pressed, because the main speaker, the main central speaker, stops producing certain frequencies which are then audible on the sides, produced by this and the other transformer. Again, you've got the 1 nanofarad across it to cut off the very high frequencies, which will be produced in the tweeter. The other thing it does is it does reduce the possibility of high frequency oscillations by having these high frequencies bleed off. You're not hearing them anyway, so why have them heat up your tube, okay? Your tube can produce those high frequencies in the hundreds of kilohertz. You just can't hear it, so you bleed them off. Now, the way the electrostatic tweeter works is very interesting. This is the screen grid of the ELL80, the one side of it, and this has got a B+. So through this 47K capacitor, a resistor, you're feeding B+ to the electrostatic tweeter. So you're basically charging it. You're basically polarizing it because the other side's connected to ground. So this electrostatic tweeter is constantly held at a high voltage potential between the two plates. And that is the perfect condition for it to then produce audio if you feed in a low-level audio signal. And that low-level audio signal comes through this capacitor from that side of the circuit. So from this anode, from this output tube, comes through there and it's fed in there, and then you hear it reproduced on here. These are the frequencies that are not cut out by this 1 nanofarad capacitor across the outside of this primary. So therefore, you've got a system which produces really a 2 + 1 + 1 system. You've got base in the middle, left satellite, right satellite, and then you've got an electrostatic tweeter for the very, very high frequencies. And these are driven, this whole system is driven with only two pentodes, where they mix a push-pull configuration with a single-ended configuration. It's very, very interesting. If you read the article that I'll link below, it'll give you a much, much better explanation. And it also explains further back as to how the preamp tube is used to drive these two pentodes, because with push-pull, you need these two to be producing inverted signals. So if you have two channels and you have the signal coming in, you've got to invert one side of it. And the way they invert it is very interesting. They use the anode of the triode in the Magic Eye tube, which is why this tube is actually positioned where it is between one part of the preamp, one triode of that ECC83 preamp and the driver tube. This Magic Eye tube is doing two things. One, it's giving an indication as to the tuning, but also it has a spare triode, so they decided to use it as an inverter with this -1 gain, in other words, unity gain, but inverting in this position. And the way it works, again, is explained in that article. Very, very interesting article. The way it works is that this resistor, that resistor, and that capacitor, if you look at it, this capacitor over here is AC coupling to the grid of this triode. This is the triode over here. So it's AC coupled to there. And the way they explained it in that article is much better than I could, believe me. I had to read it carefully to figure out how it works. This is almost like an inverting op-amp situation where you have the input resistance, the RI, you've got the RF, the feedback resistor, and they should be the same value, but you notice this one is 2.2 meg and that's 3.3 meg. The reason is you're basically producing, if you look at an op-amp and you use resistors in this of these values, you're producing a gain which is higher than -1. But the reason they make it purposely higher than -1 is to compensate for the fact that this is not an ideal amplifier with no loss. This does have losses. So the result that you want over here is -1 times what you're getting out of the or coming into the system. So it works as a Magic Eye tube and it works as an inverter. And what I'm doing next is I've started doing this. I've started going to the switches, and actually, if you look here, the schematic is very poor, and reading these annotations for the contact points on the switches is very, very difficult. Some of them you just can't tell. So I've actually checked and started creating a cleaner look. I put these annotations in here. I've actually put the function of that switch in here. So ST for stereo, TA for the pickup. This does not exist on the schematic itself. You have to look down at that drawing on the bottom left that I showed you before. I've put the normal position of the switches. So in their off state, in their naturally unactivated state, these are normally open, so I've drawn them in. And this will help us when we start trying to figure out what gets switched in and what doesn't when the operation is looked at. So that's where I am, and that's where I'm going to continue on from. You will also notice that I have these two capacitors here are the ones that I changed. These are the coupling capacitors, which were creating that very high positive voltage on the grids of the, at least the one of them was, on the grid of the output tube. So those have been drawn in. And I'm going to now go back and continue with this process till I've done the entire power amp section and can perhaps have a closer look at how that whole thing operates.